Thank you. So today I'm going to talk about what I call modern search engines. I wanted to call it 101 search engine, but I wanted to brag a little and call it modern. So that's what we are going to talk about, with an emphasis on the multimodality of the search engine. I'm Jim Ferenczi. I'm a tech lead at Elastic, working on search, previously on enterprise search, and now working on all searches. So first, let's start with a quick search engine definition. So with the trend in AI, now everybody wants to use a search engine. So what's the reason of using a search engine? So in RAG, so in retrieval augmented generation, the idea is that you want to get candidates that matches the query or that are relevant to the query. And the search engine role in that area will be to create or generate candidates that can be ranked by what we call a ranking pipeline. So a search engine is two things. It's first the first stage retrieval, so going from your data set that has millions of documents, taking a query, and trying to output relevant documents that are relevant to the query, but as fast as possible. And so the main question as someone that implements an application using a search engine is how and how many you will merge, score, and rank candidates that are retrieved by your pipeline. This operation is always a trade-off. It's a trade-off between the relevance that you want to give to your application and the performance that you want to achieve. So if you have millions of users, you don't want each query to take seconds to respond. And so that's why search engines are used today, because you want to make everything fast. So how to make it fast? The main response here is by using search engines that are designed for that. And in this presentation, I will show you hopefully as many examples as I can, because I have a lot of content and not a lot of time. But I want to show you examples of why search engines are fast at retrieving candidates and why Elasticsearch is one of the fastest, thanks to the years of development that we've put into this. So what is a search engine funnel? So we already defined that a search engine is something that retrieves candidates and as many candidates as possible. But then there is this question of how can I reduce my funnel into few documents or even one document, the best document that I can retrieve. So as I said before, so the first phase is about what we call a first stage retrieval. It's working on your entire data set. The second stage, or the stage afterward, will always work from the candidate of the previous stage. So the idea here is we call it a funnel because it reduces the number of documents that you will to rank at each stage. And because the number is reduced at each stage, you can apply something that is more expensive. Like, for instance, a ranking model that requires to look at the text of every document that you retrieve. This is not something that you will run on millions of documents, but maybe on 100, that's fine. And so that's why we use this funnel and this operation as a pipeline. So now, what are the modalities that you can use in a search engine? So here I'm a bit abusing the terms multimodality, but it's just to say that now with the trend in AI, you can use multiple types of retrieval to get your candidate generation. So the most easy one, or the most popular one, the queen and king of all, is the text. So the raw text that you can extract from your document and using it to match the query with a relevance score. The second part that is not new, but something that now is very popular as well, is all the things around vectors. So there are 2 or 3 types of vectors here. I will not try to determine which is the best, because they are like the main thing to understand here is that a search engine is a toolbox where you can mix everything together to get the best ranking. So this talk is not about choosing a specific modality to do your search, but more to show that you have all the tools that you need to make the best relevance out of it. And if we wanted to discuss how to merge these results together or how to merge multiple modalities together, that would be a completely different talk. But here, so I will try to give an example of text. So how can we make text returns candidate generation faster? I will make also an example with vectors. So here we have 2 types of vector, dense and sparse vector. The dense vectors are the ones that have a dimensionality that is fixed, versus sparse vector, where you can have more dimensions, but they are sparse, meaning that not every document has all the dimensions. The last one is the rank vector that I will introduce at the end if I have time, and they are coming in 8.18. It's a new modality that we are adding to Elasticsearch. So let's start with the most popular retrieval of all. That's called the full text search, right? So in a full text search, I start with a query. A query is just a list of terms. And so for this query, I'm picking a very simple query that is just for search. If we go inside the search engine, what happens at indexing time is that we will build what we call inverted lists. So an inverted list is for each terms that appear in my documents, I will invert their association. So instead of saying that document 1 contains you, I will say that you contains document 1. And so the one thing that will happen here is that for each of the terms that appear in my dataset, I will have a big list of all the documents that contains that term. It's easy, right? It's just IDs that are contiguous or not, and that represents documents that are present in my database. The second thing that I need for text is the frequency. So how many times these terms appear in my document. This is important for the scoring of those documents, because if a term appears multiple times in BM25 world, that means that maybe it's more important than another term that only appears once. The last thing that is important is that we may also be, we may also want to keep position around. So position around so that when I do a query, I can first probably get a score of how much the terms are close to each other, but I also can add this as a filter. I just want documents that have the term you and the term no that are at one position apart, for instance, like in a phrase search. So these three data structures, they are just 3 files on disk that contains for the documents a list of IDs for the term, then a list of frequencies. Each frequency is associated with a single document, and then the list of positions for each of those documents. As you can see, everything is separated here. And I'm talking about files here because you will see just after that this is an important design decision that we've made. So let's look first at the posting cost. So how much it costs to store these document IDs, these frequencies, and this position. If you look at document IDs, let's say that we restrict them to an integer, so 4 bytes, so 2 billion or 4 billion IDs in total, depending if you take the signed or the unsigned version. Then the frequency, so the number of times a term appears in the document, so again 4 bytes. And then the position, again 4 bytes per position. So if I do the encoding of my inverted list in a way that is very straightforward, I will get for a text with 128 positions and 64 unique terms, 1024 bytes to store, to read on every query. So to reduce the cost in storage and in memory, compression and block loading is required. And so that's really the gist of every search engine, how you will compress and how you will load efficiently these blocks of data structure. So the first thing to look at is that on every search engine, you will see the term skip list coming often. So the skip list is the idea of, I want to be able to go to any document on any inverted list in a way that is fast. So I want to jump directly to document number 68, right? The property that is very important in my inverted list is that the document ID are sorted. Because they are sorted, I can first try to lay out them into blocks. So here I'm using a block of 4. So each block of 4 contains 4 doc IDs, and each upper block contains 3 blocks, right? And so we can see that a skip list is something that has multiple levels, and at each level I have a different granularity. So my granularity at the smallest level is 4, so I have 4 doc ID. My granularity at level 2 is 12, because I have 3 blocks. And my granularity at level 0, which is the biggest level, I have all the blocks. So what is interesting here is that on each of these blocks, I can encode the min and the max of the doc ID. And then suddenly, doing a binary search on this min and max, and I can very easily determine where I can find the document that I'm looking for. And I can do it at every level, meaning that I can skip a lot of blocks just by looking at the levels that is the uppest. So that's great, but that doesn't reduce the memory that I need to encode all this document. And so, as we said, a document ID today, it's 4 bytes. So the things that we're trying to do in these blocks is how can I reduce these 4 bytes per ID to something smaller? So the first thing that I can do is, because the documents are sorted by their doc IDs, I can just use what is called diff encoding. So on the first example, I have document 0, 1, 3, 6. So what I can do is, instead of encoding 1, 3, and 6, I can encode just the difference with the document that appeared just before. And so instead of having these differences here, now I will rewrite this as 0, 1, 2, 3. Why? Because 0 is the first doc ID, 1 is 0 plus 1, that's the next doc ID 1, 2 is 1 plus 2, so 3, and 3 is 3 plus 3, 6. What I did here is I just reduce the span of my IDs. So instead of having IDs that can be big, I just reduce them. I make them smaller number. Because they are smaller, they can be encoded with less bits. And in this specific example, what I can do is I can take the biggest doc ID, which is 3. I can determine how many bits I need to encode 3. The response is 2. And so now I can use 2 bits to encode my entire block. So each doc ID can be encoded in 2 bits. So compared to the beginning, from 16 bits, I can use only 8 bits, right? So this is a very large reduction of the size of all the things that I need to read. I said that, it's a block. The reason why it's a block is because we don't want to read this one document ID at a time, because that would take a lot of time. What we want is to load a full block in one go. And that's where we use what we call SIMD. So the SIMD acceleration here would allow us to, in a single thread, to multi-thread this reading by employing the new capability of Java through the Panama API. So it's an API that allows you to leverage the SIMD acceleration. And the idea is that instead of loading all these doc ID and taking the time, one doc ID at a time, I will load them in a single block as a vector in the Panama API, and the vector will be multi-threaded, or at least parallelized in the SIMD instruction. So why do we do that? Because when we load blocks from disk. So as I said, the document, the frequency, and the position, in fact, it's 3 files that are on disk. So how can I do to load this file on disk? So to load this file on memory. So one thing that I could do is I could read the entire file and put this into my memory. And I could look at the frequency and load everything and put this into memory. Now the problem is maybe that I have queries that don't use position at all. I don't have phrase query, but I have them as maybe later I will do phrase query. So should we bother about loading all the position in memory? Should we bother about loading all the docs? Maybe that I will not look at all the inverted lists that are in my index. So the idea here is that we use what we call MMap. So MMap is a way to take all the files that you have on disk, and create virtual addresses that are what we call here the page cache. And the page cache will mean that for every part of the file that I'm trying to load on memory, I will read them on disk if they are not already in memory, and I will make them part of what is called the page cache. And so the page cache is limited, but my virtual memory is almost unbounded. It's bounded by the size of my disk. So I can have an index that is 300 gigabytes on disk, only have 16 gigabytes of memory, and every time I'm accessing something very often, it will stay in the cache. If I access things that are not very often accessed, then they will be accessed from the disk. So what does that mean? That means that from this design, we have a slow memory that we will call page fault. So every time I'm going in the document, in the file, and I'm trying to load one part of this file, I have two possibilities. One, that it's already in memory, it's fast. It's not in memory, I need to read it from disk. And so when it's not in memory, what we can do as well to make it faster is to parallelize the disk access and still using a single thread, because in fact, what we want here is to parallelize the disk access, not what we do in the thread in terms of the CPU. So it's really about the disk. And here, we are leveraging what is called the POSIX system calls, where we can ask the file the parts that we will need, but that we don't need now, but that we will need in a few seconds. So for instance, I can say, I want this block of memory, but I also want this block, and that block. And so instead of reading one block at a time, I can start the reading of all these blocks and then process them when they are ready. Meaning that I can do stuff while the blocks are still loading. And so that's where what we call the preloading the page eagerly when we are trying to do something sequential. And reading, for instance, an inverted list is completely sequential because we go from document ID 0 to document ID to the last document ID in the list. So one thing to keep in mind because of all this, the JVM memory, so the memory that is used by Java, will be segregated from the page cache. So you will have your entire memory. Let's say you have 32 gigabytes of memory in your system. If you reserve 16 gigabytes for the Java heap, then you only, the 16 gigabytes that are left are only for the loading of your index. And so the exercise here is to try to reduce the memory that Java needs so that we give more memory to the page cache so that we can load more on disk, more on memory, and we can do faster queries that need to read less on disk. The one thing important here is, for instance, if you go on our serverless and cloud offering, if you take a vector search profile, on the vector search profile, we decided that only 25% of the memory is reserved for the heap, for the Java heap, which is different for other deployments that we have in observability and security, or in our documentation where we say that 50% of the memory must be reserved to the heap. So one thing that is quite difficult in textual search is when you have a lot of keywords. So here I have 4 keywords that I want to search, and here I'm falling back into what we call the Boolean logic. So the Boolean logic is about what criteria will I give to my search. So I have these 4 terms. Is the first term mandatory? Is the second term mandatory? How many terms do I need to match to make it a match? And all this is very difficult because you don't know. It depends on the terms that appear in the query. It depends on many things. And so one thing that went to the rescue of a lot of people is what we call a weak N. So the idea of the weak N is to say that when you try to retrieve documents from a full text search, what you want is to retrieve the N documents that are the most relevant to your search. You don't care about counting the number of documents that match your query. You just want the best document. The best document means that I don't have to score every document. I just need to make sure that I will score only the documents that can enter this topic. And so in this example, I'm just showing a very high-level version of WAND where each term has a static score. So no has a static score of 2, for has a static score of 1, and search has a static score of 5. If we start the search and we want the top 2, we start from document 1 and we say that our search is a complete OR. So I'm just searching for no OR, for, or search. So the first document that matches is 1. 1 matches the 3 terms, so the score is 8. It's easy. I can continue because I don't have my top 2 yet. So if I continue, the second matching document is 2 because it has 4 inside, and the score is 1. So it enters my top 2. Then I go to 3. 3 has a score of 3 because it matches no and 4. And now my top 2 is filled. But what I can do that is very nice here, because I know that the top 2 is only the thing that I need, I can transform my search that before was just plain OR into something that is for, or, no, or search, but no or search are mandatory. Meaning that now every document that can enter the top 2 needs to contain no or search. And why? Because if you want to enter the top 2, you need to have a score that is better than 3. And to have a score that is better than 3, then you need to match whether you need to match no and search, or whether you need to match no and for. And so that's why here we are just spinning things, because now we are making the next candidate that we will check, we will add a criteria that is no or search. If we continue our search and we go to the document 5, we see that the document 5 has a score of 6 because it matched for and search. And now, because the best score is 6, I can do something even more interesting. I can say that now my search needs 4 is still optional, but no and search are mandatory, meaning that the next candidate needs to contain no and search. And so if I look at my inverted list, the next document that contains no and search is 9. Yes. And 9 is apart from 4, because here I could skip already 3 documents, right? And so that's really the power of one. The idea is that I can skip documents thanks to the rewriting of my query and make it very fast. And so if you look at 4 normally it's matching all the documents. And thanks to this methodology, I was able to switch to skip very easily documents that cannot enter the top 2. Just as an aside, the BM25 formula is not static, so you cannot have static score to each of the terms. So the idea is that in Elasticsearch, it's a bit more complex to implement this one. We call it block max 1, and just to give you an idea, because the term frequency that I didn't put into this example is important, so how many times the terms appear in the document to get the score. I'm just showing here that the block max 1 is about also storing the maximum term frequency that you can have inside the block. And so the idea of block max 1 is that instead of skipping candidates, we can skip blocks. So if you want more, you can read the full paper. That is very interesting, and that's one of the reasons why textual search is not as easy as it sounds. And if you look at Elasticsearch implementation, you will see that a lot of search engines are missing this feature. And in fact, they are obliging you to score every candidate in a Boolean search. I will stop here because I'm running out of time. But for next session, maybe, I will show another example with dense vector. The idea here is really that the search engine in general, they are full of data structures that are very interesting to look at. And the main usage that we have at the moment is very interesting because it's evolving every day. So look at the new things that are coming to Elasticsearch, and happy usage.